And so how do we get to there, to actually building Doom in TypeScript? We need some important tools. We need to understand how TypeScript types can be used as a programming language. And so this might be a bit hard to read. Let me see if I can zoom in a little bit. Let me zoom in just a little bit here. So there's a couple of things about this first expression on the board here. So we've got, on the right-hand side, you can see we've got conditional types, and you can use something called some type extends other type. And it looks like a ternary operator in JavaScript. And therefore, we can use this as an if statement. On the left, you can see we've got using generics, and we can kind of use those as variables. And then this last expression down the bottom, list node is equal to, and you can see there's a list node in there. This gives us recursion. It's kind of like loops. And so with this, it's pretty powerful. We can kind of set up and do whatever we need to do. So let's go through an example of how can we build a converter from snake case to camel case. And so we can use this. Let me see if this does this draw. No, it doesn't draw on the screen. We can use this type called camel case, and you can see the first variable is called remaining. So we're actually going to iterate through a string, and that string could be something like some underscore thing. And we're trying to make that camel case to something. So the first generic is remaining. The next one is a Boolean, which tells us if the next one is uppercase. And then we're going to store the result. So if we go through to the next line, we can see remaining extends, and then we can use template strings, sort of like we would in JavaScript. And we can use infer keyword almost to store these things in the variable head. So the first letter of some underscore thing gets stored in head, and then the rest gets stored in tail. And as we go through this, we can now do our first check. If head extends the separator, so in this case, for camel case, the underscore, we can then use recursion. We call camel case again. We call it with the tail, and we call it with the result, but we strip out the underscore there because you can see that the head, so the underscore in this case, isn't in that camel case expression. And so if the next part of the expression, so if it's not the separator, but is next uppercase is true, then we can actually capitalize that letter using a built-in type called capitalize. And so we append them together, and in that remaining variable, we build out our expression, and the tail gets appended to the start. And so at the end, once everything's done, if infer head and infer tail are false, that means it's an empty string. So therefore, we can just return the result. So from here, this is a program. It works. You can actually build this type snake to camel case program. But of course, with anything, you want to actually build tests for anything you build, any programs you build, because otherwise it's going to be frail. I've built an expect and equal. We don't need to worry too much about the proofs, but that's a starting point for us to build whatever we need. So we can build a bunch of tests around this. So we can check our first condition, some underscore thing is equal to something. We can also check the error cases using TS expect error. For example, some underscore thing should not equal some underscore thing. We've put it through camel case. It also should not equal any, and then we can check some more boundary conditions. What if we have multiple underscores or multiple underscores throughout the characters? So great, we've got tests now. So if we want to refactor that horrible expression you saw before into smaller little ternary operators, we can, and we can do it safely. There's a number of other libraries out there which support type testing by default. Go have a look for them, but it's great that this is actually supported. And so let's get into how we're actually using that within the editor. And I'll just put a bit of context of what is the editor? What is Atlassian's editor? If you've ever worked with Confluence, with Jira, with Bitbucket, our editor is everywhere. This is the Confluence one, which is probably our most powerful variant of that. You can drag things in, you can add emojis, images, tables, layouts, all sorts of stuff, and move it around as you expect. And so we build it across our products, and it's a big challenge. One of the things that we used to have is we used to have a React component that held all of these features, and we would toggle them on and off. There were 120 props for that React component. Imagine managing that and all the branches, right? Like, and what this means is that's our coupling diagram. This is all the plugins talking to all the plugins. That's a nightmare. We weren't happy enough with that. It also means that all products, even if you just want the most basic editor possible, you're incurring a 5 megabyte cost. That's insane. That's insanely heavy for something very light. And so we built this, the composable editor, and what this is, it's limited props, as you can see, to get you started. And you use this pattern, this declarative pattern, to add your plugins to the editor. And this is highly extensible, so you can use our plugins that we build. You can also build your own. And some products do this. It's highly flexible. And it's also significantly smaller, 70% smaller, because you just ship exactly what the consumers need in this case. And so there's a couple of problems that we found is, well, how do we make sure that consumers are safely putting plugins together? And so we built this type, we call it editor plugin, that declares some characteristics of each of those plugins. So these are like features. So imagine, your list, your emojis, your mentions, your media, all of those have one of these plugins associated with it. So they have a name, they have what other plugins they're dependent on, they have some actions, so like an API that you can call things like inserting a list or whatnot, and they have some shared state. And so this is enough to do some really cool things with. So using some of those patterns we talked about before, we can now say, well, tables actually depends on a number of other plugins. It needs the APIs of width plugin. It needs the APIs of this content insertion plugin to insert. And so you can see when we comment those out, or we bring them back in, that statically we can determine what we're missing. And it will actually create this error message. So we're using one of those programs like we used before with Snakecase to iterate through all the dependencies that are in the preset and determine what's missing. So this is one really cool thing. The other thing we can do is type-safe queries. So we have this API that also comes out of the editor, and based on what you give it, you'll be able to access different plugins, different features, different APIs. So for example, in this very simple editor, we've added things like width, tables, selection, and whatnot, and you can see there that those are the things that show up. So you can start querying deeper into those. And as you go through and use our dot syntax to like dig deeper into the objects, TypeScript will naturally tell you, oh, this content insertion just has one method, insert, right? And so in a type-safe way, we can actually access methods and things based on what exists in our preset. Another cool thing that we've got going with this is, for example, for state, we use a React hook. We need to interact with React sometimes. And based on the plugins that exist in React, we actually have a type-safe way of saying, hey, if you've got a list plugin, these are the state it has, just based on that initial type. And we go through, loop through, and allow and build out sort of this type union between all the possible combinations. And it gives you the result type as well. So everything is type safe. Okay, this is pretty cool. There's a bit of magic going on here. You should see the 1,000-line TypeScript file that builds this. But why did we do it with types? There's a number of other ways we could do it. Say we've got this simple editor. Sorry, this has come out really light here. In the simple editor, another way we could do this is just have an insert list command that you export directly from the package, right? Just normal JavaScript, export that command, and then try to use it in certain places. But what if list doesn't exist in our preset, right? If it doesn't exist, we then need to do runtime checking, right? Another case is, for example, this is our what we call type ahead. And that's its own plugin. So it builds a UI which allows you to insert different elements or different nodes. And our list plugin, for example, depends on that because we want to add our list, for example, our list node to the type ahead so that you can insert it from there. And so because it has that dependency, we can just call type ahead dot add to list, right? The other way we could do this is if we were just using JavaScript without types, we could just have a command that you export and use. Again, we have the same problem. You don't know if lists actually exist. You don't know if type ahead actually exists. So you need to have runtime checks, but you also increase bundle size, because as soon as you're exporting and importing to packages, you're coupling those packages together. So not only do you have runtime checks, you're increasing the bundle size because you're dependent on those things. So with types, they all get stripped out at runtime. So you have the static analysis in place. Types have limitations. How deep you can go for inference and whatnot can bite you depending on what you end up doing. And you might get messages like these. And you may ask, how the hell did Doom do it? If you look into their source code, they patched it. They've actually just removed the instantiation depth, but still freaking awesome. And what about the future? Like, what does it look like? As of not even a week ago, there's a 10 times faster TypeScript compiler that Microsoft is releasing. They're saying mid-2025. And it's been rewritten in Go. So this is really exciting for these sorts of things, for anyone who uses TypeScript in any projects. Very exciting news. For example, in the VS Code repository, that's 1.5 million lines, goes from 80 seconds to compile to 8 seconds. So very exciting for large code bases. And so some takeaways from here are, just go check out that video, please. It's awesome. They've got some more coming up in that series. If you want a challenge, try and build tic-tac-toe in TypeScript. It's really fun. That'll keep you busy for a few hours. And yeah, TypeScript's awesome. So keen to see what you build with it. That's it from me.
Thanks, Stuart. A bit of a round of applause, Stuart. Thank you. And have we got any showing of hands in the room to ask some questions? I'm sure there are folks out there who want to know what's going on.
We definitely have some questions. I certainly have one myself, if you want to stick around for a little bit. You have to use the lectern mic if that's okay.
Yeah.
Yeah, wow. That's actually incredible. I'm curious about the performance. Obviously, you sort of did touch on that at the end with the faster compiler and everything, but what is the performance impact of this? How do you even measure performance of the TypeScript compiler? Is there tooling for that? Is that something you are really conscious of, or?
Yeah, look, it's a really good question. We do have some telemetry that tells us how fast TypeScript is building, and so we can monitor that over time and see how it grows. We do have some optimizations, but we're really excited about the 10 times performance improvement. At the end of the day, yeah, it is a trade-off. Every decision you make is a trade-off. For now, we're comfortable with that decision. There are some optimizations we're trying to make as well, you can limit inference in some cases or try and strip types in some cases as well. So yeah, that certainly helps towards improving performance, but it's something we monitor and are aware of. Yeah.
Is there a challenge there around the fact that, because you said anyone can build a plugin, could anyone potentially create a very badly performant sort of type in their plugin if they? I mean, I guess that's their problem then, right? If they,
yeah, no, exactly. I mean, here we, we have help channels and we're aware of sort of what people are doing, and we are there to help and try and make sure people are using the tooling as best as possible. Definitely a use case with anyone extending, even outside the TypeScript, anyone extending the editor and trying to build something. There's always risks of introducing, friction, unperforming code. And yeah, we're there to support them within Atlassian. But yeah, it's definitely something to be aware of.
Yeah, I guess it's a fair trade-off, because if you're taking that performance hit away from user machines onto developer machines, which generally are more powerful anyway, that's probably an acceptable trade-off to make.
That's really what we got to. Yeah.
So, all right, anyone else? All right, I guess you just explained everything so clearly. That's amazing. Awesome.
Thanks, Stuart. I hope to see you again very soon.